Hello, and welcome to our second lesson on Einstein's relativity. This time we are taking a closer look at the first of the problems that Newtonian mechanics could not resolve, which led to the rise in acceptance of the theory of relativity. Specifically, we are looking at problems with Mercury's orbit. To get into that, we're going to have to first talk about orbits in general, and then we'll talk about Mercury's orbit in particular, and what the problem was with it. So orbits in general. Orbits are elliptical, not circular. The sun does not appear at the center of a planet's orbit. It's actually a little off-center. So ellipses have a longest diameter, called the major axis, and a perpendicular smallest diameter, called the minor axis. They would intersect at the center of the ellipse. The sun would appear at one of the two foci, singular is focus, and these are points that are on that longest diameter, equally spaced about the center. The more spaced out they are, the more elliptical it becomes, the more like an oval it looks, and the less like a circle. On the other hand, rotating objects like stars and planets bulge in the middle due to their rotation. Objects try to travel in a straight line, or really they have inertia. So in order to get them to bend into a circle, you have to constantly be applying a force. When you have a planet, the further you are from the center, the greater the force you have to apply. So it tends to bulge. This is the same phenomenon that causes something to roll across the dash of a car when you go through a traffic circle, or you turn a corner. The object on the dash is trying to go in a straight line, and the car is moving underneath it. So if you were to go from the center of the Earth to a point on its surface at the equator, you'd go a greater distance than going from the center of the Earth to a point at its surface at either the north or south poles. The same happens in stars like the sun when it's rotating. So this bulge in the middle results in something called precession. So the position of the major and minor axes of a planet orbiting a star in space will rotate over time because that star bulges in the middle. This precession is slight. It's usually measured in arcseconds per century. Now, when they first started doing astronomy, they were doing this so long ago they hadn't adopted decimals yet. So they were breaking things into fractions. And they weren't even really thinking them as fractions, they were just dividing them into more segments. So 1 degree was divided into 60 seconds, or 60 segments called minutes of arc, and each of those minutes was divided into 60 more segments called seconds of arc. So it's actually a very small segment. 1 second of arc, or 1 arc second, is 1/3600th of a degree. And precession is measured in how many of these arc seconds per century. It's a pretty slight effect. So Mercury's orbit in particular. This is actually a scale diagram of Mercury's orbit. If you take out the sun, most of us would look at that and call it a circle. We wouldn't recognize that it's slightly wider horizontally than it is vertically. With the sun in place, you can kind of see that the sun is off-center, which helps you figure out that this is an ellipse. This diagram shows the expected precession, or the rotation, superimposed on the predicted orbit. We don't see the black circle underneath, we just see the red. So the change is very slight. So what's the problem? Well, the problem is that the predicted precession in Mercury's orbit was 531 of these arcseconds per century, and that the observed precession was 574 arcseconds per century. Doesn't seem like a huge difference. We're looking at 43 out of 3,600 degrees for each century this is going. So it's a difference that would take over 8,000 years to make 1 degree. But every scientific measurement has an accepted margin of error, and this difference was greater than that. They had measured Mercury's position to a much greater degree, and they knew that the theory they had was not consistent with what they observed. So that every scientific measurement has what we call a margin of error. I don't like the term error, I prefer uncertainty. Error implies we've made a mistake. But if you think about measuring something with a meter stick labeled to the millimeter, or a yardstick measured to or labeled to the 16th of an inch, you're not going to measure something to the micrometer or to the 1600th of an inch because the tool doesn't measure that precisely. So that's where the margins of error come in. And there is what was expected and what was observed, and they were not consistent with each other. So if we look at the three of them, here I've got all three graphed. The observed rotation is in blue. We can only see the blue. So I do want to keep things precise and specific in these lessons, but in this case, we're going to have to move to a fictional orbit to get the point across. So this orbit is far more elliptical. If we look at where it is now, this is a fictional orbit with one amount of precession, what was predicted, and the blue is what was observed. So we could see it's not the same thing. These orbits have been shifted. And that's the problem. Mercury's orbit was rotating faster than Newtonian mechanics could explain. So that is one of the problems. I'm not going to dig into the solution to it until we get to that stage much later in these lessons. We're going to explain the theory of relativity first, and then show why it gained the support. So up next, we're going to look at another big problem. We're going to look at the Earth and its motion through the ether. The ether is something that Newton proposed because he recognized limitations of his model. And they spent centuries trying to identify the ether and how the Earth was moving through it. And that search was pretty fruitless. We are going to talk about how that search came about, how it was transpiring, and what we ended up doing instead.